I was really surprised to see so many of you coming to attend this lecture this evening in the nice weather. And I think you know that I'm going to talk about superconductivity. And what I know that in Japanese universities, in the Department of Physics, they say it is very difficult to teach superconductivity to physics students to understand. And according to the poll, they graduate from physics department, 60% of them graduate without understanding superconductivity. So I hope you understand superconductivity tonight and about the importance of superconductivity as well. I would like to introduce to you about 100 years of development of superconductivity in the first half, and then in the later half, I would like to talk about what we expect to happen in 100 years from now. It was exactly 100 years ago when Kamerlingh Onnes of Leiden University in Netherlands discovered superconductivity by observing the resistivity of mercury suddenly drops down at the temperature of liquid helium. But what I am impressed by his work is that it's not just the resistivity went down, but also he observed the perpetual current or permanent current flowing forever in a ring of superconductivity. This is even more impressive to me. The character of superconductivity is that we have exactly no resistivity in the superconducting state, and also we have so-called Meissner effect. That means superconducting material exclude all the magnetic field outside of the superconducting body. And we have so-called Josephson effect, with which a superconducting device can work like a transistor with much less energy. So these are the three miraculous characters a superconductor can exhibit. Since the discovery of Kamerlingh Onnes, there are many properties of superconductivity found until 1950. But the mechanism of superconductivity was not understood for about 50 years after discovery. And it was gradually said that superconductivity is the most difficult or most challenging physics problem of 20th century. That's what physicists started saying. In 1950, phenomenological theory was developed by Ginzburg-Landau school. They called Landau school about the people who worked together with Dr. Landau. And Abrikosov was one of them, and he developed the concept of vortex. And this picture is the first image of Abrikosov vortex lattice, which was observed in 1967 And this became a very important observation later for superconducting material scientist and superconducting engineer to fabricate superconducting wire. Because of the development of Ginzburg-Landau theory, we understood superconductivity in the sense that superconducting material, electron behaves like a big wave which is coherent everywhere in a superconductor, just like the laser light. And in case of normal metal, the electron is also behaving like a wave, but it's individual, and the wave is not coherent at all. So this coherency of the electronic wave in a superconductor is a very important function. And we had to wait until 1957, about 50 years after the Cameron Onnes's discovery of superconductivity, to really understand the microscopic mechanism of superconductivity. It was BCS theory established by Bardeen, Cooper, and Schrieffer, based upon the concept of so-called Cooper pair. Electron becomes paired in a superconductivity, and so-called Bose condensation of Cooper pairs. These are the two important ingredients of the microscopic BCS theory. And we then understood why it was so difficult to understand the superconducting mechanism. It was not just the understanding of the quantum physics, but we also have to include many body or n-body idea into our quantum mechanics understanding. Until 1986, Einstein explained to us, what happened in 1986 in Switzerland, and until this year, it was the era of metallic superconductivity. Although metallic superconductivity was still powerful, but we had limited number of applications, because the critical temperature of superconductors was well below liquid nitrogen temperature. And we had to cool down superconducting substances with liquid helium. And liquid helium cost much more than liquid nitrogen. 1 liter of liquid nitrogen costs like 10 cents per liter, whereas liquid helium costs like $10 per liter. So it was not very easy to cool down superconductors with liquid helium. But even so, there were some applications of superconducting materials. The most common commercial application is this one. This is called MRI, magnetic resonance imaging, in which human body can be inserted inside of a superconducting magnet. And you can get this sort of image. And this is a blood cell of a person. This is a heart. And this MRI imaging is based upon completely different principle from X-ray imaging. So both X-ray imaging and MRI imaging can give us very useful information of our body. And another application of superconducting material is this one. And I was very fortunate yesterday that I could visit CERN accelerator facility. And if you go there, and if you are fortunate, you can go underground just once, 2, 3 years. Okay? And inside of the tunnel, you have a series of magnets, many magnets connected, and particles can be accelerated in the tunnel by using this magnet. The magnet can make it, in a circular shape. And if you accelerate particles just want to go straight. But in order to make a circle, you have to bend it. And superconducting magnet can do it with a strong magnetic field. And also, in the CERN accelerator facility, you have many high sensitivity detectors of particles, which is composed of many superconducting magnets as well. So this is a very nice example of applying superconducting magnets for the research of high level of science. And I think that Switzerland is a very fortunate country to be able to construct this sort of a high level of scientific facility. And now let me introduce to you a little bit about Japanese magnetic levitation car, which is running on the test line near Tokyo. And this is maglev, which is being developed by Japan Railway Company. And if I ask children, what is different with this train from the other trains, and they immediately can tell me what is the difference. Okay? And perhaps, there are no children here, so I don't think you understand. Okay? The bigger difference is that this train does not have pantographs. Okay? And the reason why this train does not have pantograph is because this train does not need power on the train, but still it can run. And this is because of the superconducting magnet. So on this maglev, you have superconducting magnet here in the car, and on the tracks, you have two kinds of coils. Okay? These are made of normal copper coil, not superconducting coil, but copper coil. And these sets of coils levitate this train by repelling the superconducting magnet upwards. While this train runs at a speed higher than 110 kilometers per hour, the superconducting magnet, which is operated by perpetual current, permanent current, this magnet creates induction current in these coils. And this induced current repels the superconducting magnet from from underneath, from this side, and it pushes up. And then we have this propulsion coil. And this propulsion coil pulls this magnet always forward. So if it is any polarity, this coil just in front of the superconducting magnet becomes S polarity and pulls this magnet forward. And when it passes, then this polarity changes N, so that to push the magnet forward as well by detecting the position of the train. So what you do is that in this propulsion coil, you have many propulsion coils, and you pass alternating current, AC current, on these coils, so that the train always is pushed forward. And also these coils, because it operates on the induced current, if the magnet of the train comes too close to this side coil repels the train more. So the train always goes in the center of the trail. So you do not need to adjust at all about how to guide this train at the center. This superconducting maglev has been developed by Japan Railway Company for these 50 years, and with the intention that they wanted to create very safe train than the conventional one. I once met the engineer who started this project, and he said that train now in the present day is not perfectly safe, because you have a rail on the ground and there are wheels rotating on the rail. That means this circular wheel touches the rail at one point. So one point contact. That means all force is concentrated at this point, at the contact point. And because of this, we have stress concentration at the point, which usually materials do not like, to have a very big force at just one point. But in case of magnetic levitation, the volume near the superconducting magnet, the volume around there, pushes up the train, so that there is no one single point in contact. And in case of maglev, the clearance from the ground is about 10 centimeters. So even if you have some stones on the trail, still you can run the train because of the clearance of about 10 centimeters. And in case of conventional train, there are some limit of traveling speed. But in case of maglev, there are no speed limit. But if it runs too fast, then because of the air turbulence, you get a big resistance from the air, so it's not energy-saving train anymore. That's why the business speed is set at 500 kilometers per hour. Well, because it can run at 500 kilometers per hour, and if you put a tube around the train, it can run even at 2,000 kilometers per hour. So in the future, we can imagine the maglev train running on the Earth instead of the airplane. Airplane, the speed of airplane is about 1,000 kilometers per hour. So maglev can even run faster than a jet plane. So it is always very enjoyable to think, how we put this sort of trails based upon, in this case, I just put lines on considering the population density on the Earth. So application of superconductivity based on metallic superconductors started with this sort of facilities. And as I told you that by 1986, the critical temperature of superconductivity was well below liquid nitrogen temperature. So in order to apply superconductivity, we have to use liquid helium, which is expensive. So the superconductivity application did not become very popular. So everybody wanted superconductor with critical temperature above liquid nitrogen. And I was one of them. And everybody, if you are working on superconducting materials, wanted superconductor of critical temperature above liquid nitrogen. It was a dream for everybody. And all of a sudden, it started because of Bernoulli and Mueller in 1986. These are the superconductors by 1986. And Bernoulli and Mueller started this trend because of their discovery of cuprate high-temperature superconductors. Cuprate means compound composed of copper and oxygen and something else. And once they discovered the cuprate superconductor, we changed the composition, and we could go up the critical temperature very rapidly, and so rapidly, so we even dreamed that the room temperature superconductors may come. But unfortunately, although it went up so sharply up, but the highest is about 160 Kelvin, and the practical material we can fabricate is this one. One is bismuth system, and the other is yttrium system, and it's around 100 to 120 Kelvin superconductor. So slightly higher than liquid nitrogen. So of course it is much nicer to have liquid, to have room temperature superconductor rather than liquid nitrogen superconductor. But still, it was a great discovery, and it has become much easier to cool down superconductors. That's why all around the world, they were so excited in those days, in 1986 and 1987. This is Time magazine, and this is Science magazine, all talking about the future dream of superconductivity. And it started with this paper. Bernoulli and Mueller wrote a paper in a magazine called Zeitschrift für Physik. And with the title, possible high TC superconductivity in the barium, lanthanum, copper, oxygen system. They said possible because perhaps they could not completely, they were not completely sure, or they could not completely prove that there was a superconductivity in their sample. And then I was interested in their work, and my student worked on their sample, on their material. Bernoulli was an expert chemist, and my student was just an undergraduate student. So Bernoulli synthesized the sample with a sophisticated chemistry, and my student worked to fabricate the sample by just mixing the powder in a mortar. So the composition finally they got was different. And my student was very lucky because his material has different composition. So in his case, we got even better superconducting property. And we then could go to a pure composition of superconductivity. That was of the composition, lanthanum, barium, copper, O2 composition. Excuse me, here. Lanthanum, barium 2, copper, oxygen composition. So we could obtain very beautiful Meissner signal. Meissner signal is this one. At below 30 Kelvin, it becomes to show Meissner signal, that is diamagnetic signal, which the superconductivity expels all the magnetic field outside of the body. And we could observe the X-ray diffraction pattern in order to identify the crystal structure. And we could reach zero resistivity for the first time above 23 Kelvin, which was the highest record critical temperature by then. And I announced about this in December, as Oystein just mentioned, in Boston at the MRS meeting with this crystal structure figure. And in an American book published in 1987, it describes in the cover story saying that in Boston, I talked in an MRS meeting about the latest news from Tokyo, and after that, it says that their old research, I mean the audience's old research, would be put aside. It was a whole new ball game. That's how they described in this book, in the with the title, The Path of No Resistance, with the author H. Schechter. Our lab at the University of Tokyo was like this in those days. There were even cartoon books published in Japan, and students became the heroes, whereas professors were described like this. This is supposed to be me. So students were very happy with the cartoon books. But the good thing with the cartoon books published in Japan is that they had lessons for every people, for everybody, to teach about superconductivity, to teach about magnetic levitation. So it was very helpful. Once I got an interview in the United States in a magazine in 1988. And I got an interview like this. Your primary goal is to discover the mechanism. And your hope is that it will never be discovered. Perhaps I told them that I don't like the mechanism of high temperature superconductivity be really, understood. The way I answered is that, right, you might say my feeling is very complex, but I'm sure you understand. A mysterious woman is always more attractive to a man. That's a way, perhaps, I don't know I really answered in this way, but I am sure that I could say that the superconducting mechanism of high temperature superconductivity is still not well understood by now. So that means I am still very happy. In this way, the discovery of high temperature superconductivity was very much welcomed by people. But there was a serious problem associated with high temperature superconductivity. And this is rather a professional problem, but in a short sentence, the coherence length of a superconductor is too short compared with a conventional superconductor. That means Abrikosov vortex is the guiding principle for us, as I told you, and we have to fix down this Abrikosov vortex at a point. And if the Abrikosov vortex moves around, we have finite resistivity. So we have to pin down the vortex. But this becomes very difficult because the coherence length, that is the effective diameter of the Abrikosov vortex, is too small. It is in nanometer scale. That means we have to control the material in nanometer scale. So this is nanotechnology. Although it is still very difficult now to control the structure of a substance in nanometer scale, but now material engineers have been working very hard, and they have become partially successful. And they have found out various ways to fabricate the superconducting wire. It was only the year 2005 when the performance indicator exceeded the target. The target we were working for the performance indicator, which is a product of critical current which we can pass through the superconducting wire, and the total length of the wire. So this product is very important as a performance indicator. And only 2005, that means 20 years after the discovery year was here. So 20 years was necessary for materials engineers to reach the target for the performance of the wire. And then, for the first time, we could start manufacturing systems like this one. This one is a ship propulsion motor. Here is a superconducting motor to rotate the screw for a boat. And before then, because of the small current we could pass through a superconducting wire, this motor became too large. So the screw was hidden by the big size motor. So it was impossible before the year 2005. They started to try manufacturing various things, like in this case, NMR is an analytical tool for, especially for chemists. And if we can have higher magnetic field, they can go higher detection limit. And high temperature superconducting coil can be inserted in a superconducting, conventional superconducting magnet to intensify the magnetic field, to reach higher magnetic field, to create better resolution for the chemistry analysis. And they have started various projects to fabricate motors and electric generators. These are Japanese projects, Korean project, Siemens in Germany, American Superconducting Corporation, and American companies, Siemens, and American companies as well. And these are the companies which have been trying to fabricate motors and generators. Some companies, this one is by Sumitomo in Japan, tried to test putting superconducting motor inside a car to make a superconducting electric vehicle. They have been trying to manufacture superconducting cable. And in case of superconducting cable, you pass liquid nitrogen flowing inside of the cable. And it can flow for distance like 20 kilometer to 50 kilometer. So at each interval, you have liquid nitrogen refrigerator to fabricate liquid nitrogen and pass this liquid through the cable. And then again here, you create liquid nitrogen to pass again through the, through the cable. By doing so, you can cool the superconducting cable inside the tube with thermal insulation around. And by doing so, they have been trying to make the power capacity as big as possible. And at the current moment, the highest one has reached 66 kilovolt, passing 3,000 amperes. And in the near future, they think that they can pass an electric power which is created by a big nuclear reactor. This is 100 million kilowatt, okay, just by one single superconducting cable. So a superconducting cable is very powerful in that sense. And because, you know, a superconducting cable can pass more current comparing with the conventional power transmission underground cable, it needs just a small cross-sectional area. And in case of Japan, the land cost is very expensive. So small cross-section of cables is very important. And they say that the cost of power transmission is becoming less expensive with superconducting cable than using conventional cable. And besides, some say that in case of copper overhead transmission cable, sometimes thieves come and steal the copper wire in order to sell. But in case of a high temperature superconductor, thieves do not know how to sell. So they say that it's better. Anyway, this is how they installed high temperature superconducting cable into the duct. This was made in Yokohama substation in the summer this year. So I think these are the area where we can put power cables underground. We can start from this sort of area. And because of the great discovery of Bernard Mueller, the applications of superconductivity are expanding now. I am paying special attention to this sort of application in these days. When you generate electric power with solar panels and windmills, it is easier to collect the electricity in DC mode, direct current, not alternating current, not AC current, but DC electric current is easier to collect from those small generators like solar power panel or windmills. And usually the voltage is low, and if the voltage is low, we have to pass a large current because voltage times current is the power. So if the voltage is low, the current should be large in order to have the same power. And if the current here is very large, it is better to use superconducting cable instead of copper cable because of the large current, electricity is dissipated in the copper wire. And besides, additionally, in these days, DC inverter, DC electric converter is becoming much easier than AC inverter because of the development of semiconductor devices. And so DC electric power transmission by using underground superconducting cable, I think this is a good trial in the near future. In Chubu University, near Nagoya City, they have installed DC superconducting power line. This is a test line, and this is a terminal. And they are trying this DC power transmission line so far successfully. And now let's think about our Earth, the global Earth, and if we have superconducting power cable connecting from the west to the east, what happens is that one side get sunshine, while the other side is dark. Solar panels do not work on this side. Okay? But if we have superconducting cable, we can average day and night. And if we have superconducting cable in this direction, one side is summer, the other side is winter. And electric consumption is very different in summer and winter. Okay? So we can average the consumption as well. Connecting windmills and solar panels, the serious problem at this moment is that windmills generate electricity only when wind blows. And solar panels get electricity only when the sun shines. But if we have this sort of superconducting connection around the world, what then can we expect? Intermittency of wind and solar panel will be gone, and those energy sources will become an ideal energy sources. So the Earth appears to be happy. And again, I always like to draw this sort of picture, and I am dreaming also. But in these days, there are many people who are drawing this sort of figure. And I think, there may be somebody here, who tend to worry. Okay? There are some people who are very optimistic. And then if you are very optimistic, you just say, okay, it's very nice. And if you are rather pessimistic, you might say, what would happen if terrorist attacks and cut the superconducting wire? And then the answer is that we should have multi-connection, as many as possible. Then, terrorists cannot cut every cables. And that's one answer. And the other answer is that we produce hydrogen when we have enough electricity and store them and use hydrogen if we have any problems. In that way, we can have stable energy, stable electricity. And perhaps I think you know that the Earth has a geomagnetism. And geomagnetism is such that very fortunately, this geomagnetism is protecting us from attacks by the charged particles in the cosmic ray. So unless we have this geomagnetism, cosmic ray directly arrives at the surface of the Earth, damaging the genes in our body. So that means we cannot survive anymore if we lose geomagnetism. But what is said in these days is that we are losing geomagnetism. And in 750 years, it is said that geomagnetism decreases to 1/2 of the present value. And the mechanism of occurrence of geomagnetism is not known yet. So there is no way to prevent it either. But we have the answer. Okay? We round up the Earth with superconducting cable, and we pass the perpetual current to compensate the loss of geomagnetism. And when we did the calculation, I can say that this is not very easy. Not very easy, but it is possible. Okay? If, more than 1,000 years ago in China, they built a great wall, the Great Wall. And if we pay that much of effort, I'm sure that we can construct this scheme to protect the cosmic rays to arrive at the surface of the Earth, even if we lose the geomagnetism. So this is another reason why we have to have global superconducting grid. In addition, for the purpose of utilizing natural energy like windmills and solar cells. And with this, the Earth will become very happy. Thank you very much for your attention.
Thank you very much, Koichi Kitazawa, for a very clear and complete explanation of where we are today and telling us about your visions for the future, the long-term future. This talk is now open for questions and comments. There will be persons going around with a microphone. So if somebody wants to ask a question to Professor Kitazawa, please raise your hand and make yourself known. Yes, I see a question high up there. Could somebody bring the microphone up to the person? So we are still waiting for the microphone to come. Okay, here it goes.
Well, my question is, you have a very fast train that goes very fast and so on. What do you do to stop it? How do you stop the power of superconductivity in a way that doesn't make any damage? For example, there's a cow in front of the train. How do you stop the train when it's at 500 kilometers an hour?
Okay, you got the question?
Yeah.
Yeah.
We are very optimistic in this sense, and we do not hope cows coming into the trails of the Maghreb train.
Yeah, but anyway, how do you stop it?
I mean, how do you brake?
But in order to stop the train, it just the same thing, propulsion mechanism did. Ahead of your magnet, okay, it was S polarity when to pull, but then you can make it N instead of S, okay? Then the car gets brake.
Okay, does that answer your question?
More or less.
More or less, okay. Good, maybe we'll see if I see a question up here. Please, could somebody bring the microphone up there?
I've got also a question to the train, to the magnet supraconductivity train. If you want to use metallic things in the train, will they fly around because of the magnets?
Uh-huh. The answer is, the superconducting magnet is enough far from where the people is in the train, sits in the train. And the place where you walk, the highest magnetic field is like 20 Gauss. It's, the geomagnetism is 5 Gauss or so. Okay? So it's not very strong, the magnetic field inside the train. And you shield the magnetic field with using iron.
Maybe you could say something more about the train that you showed actually is working with people in it already, right?
Yes.
Yeah. So there is a complete train, like a normal train, actually flying 580 kilometers an hour down the line with people inside. So these things are already tested very well out.
I once rode, this maglev, and it was like just riding in experiencing the Shinkansen, the bullet train. So TGV, is about the same feeling you have to be put on a TGV.
Okay, we have a question here. Alan Williams.
Many superconducting materials use rather rare elements like yttrium, and we have already seen that rare elements can suddenly become very rare, as we saw with the rare earth elements. Do you think that the resources in the world are sufficient to make enough cables to run around the world 5 times?
Well, for example, in case of bismuth copper oxide system, bismuth, I think, is more abundant than copper. And anyway, we need either copper or aluminum, okay, in order to have power transmission line. And we already have a lot of power transmission line, already. That means, we can change this copper, to the superconducting wire. And we then have copper, and we have enough bismuth, compared with copper amount.
Okay, are there other questions?
So what I mean is that we do not need more materials than ordinary copper wire.
Okay, I'm looking around. Yeah, I see a hand raised up there. Could you bring the... Could you just wait for the microphone so that we can all hear?
Are there any applications of supraconductivity in computers? Can we build better computers with it?
There are lots of efforts paid, to create a superconducting computer, especially based upon so-called single flux quantum, SFQ device, single flux quantum device. But so far, they say that there are some difficulty to make memories in a very, condensed way to make like large-scale integrated circuits. We cannot make it enough small yet, each device. So they still have some difficulty to make the superconducting computer as effective as semiconductor computer. Although, in principle, they have been able to show the basic functions, but it's not as effective yet as semiconductor computer.
Okay. Is there one more question? Yes, I see one up here. Could you please bring up the microphone?
Good evening. Has there been any cost about 1 kilometer of supraconducting line, and how much it will cost the maintenance of that?
Could you please speak up a little bit and try? It was hard to hear.
Has there been? Does it work? No. Has there been? Yeah. Any study about the cost of 1 kilometer of supraconducting line, and how much it will cost?
Okay.
I am not sure about the cost at present, okay? But at least they say that comparing the superconducting power transmission cost as a whole, as an underground power cable, superconducting cable and ordinary cable, considering everything, they say the cost is about the same now. But at this moment, superconducting wire is not produced in large scale. So if the demand becomes large, they say that the cost comes down even more. But in case of a conventional cable system, the cost will not go down anymore. So we are not worrying about the cost of a superconducting cable.
Thank you.
Okay, I'm looking around. There's still one more question. I see one here. Please. Yes, here.
Good evening. I have a question that goes a little bit in the direction of the one before. What about, liquid N2 is very cold. So what about the risks if the cable breaks, if there's something happens? What about the environment if there are some problems with the lines? What about the electricity is very, very high in the superconducting cable. If it is touched by someone, what to do to prevent all these things? Are there any solutions yet? Or?
Yes, it is dangerous. Okay, but with a high voltage power transmission line, if you touch, you'd instantly become dead. Okay, so in that sense, electricity is dangerous. So we avoid to touch on electric cable. Okay, this is but always necessary, even now. And the superconductivity does not change this danger. And only liquid nitrogen may be different thing. And what they say is that, although I'm not an engineer, in cables, but what they say is that even now, underground cable of copper wire transmission is cooled by water. So they are running water inside of the manhole, okay? And they pass water. And comparing with the water cooling and liquid nitrogen cooling, they say that it's more dangerous with water because water is partially electrically conductive, but liquid nitrogen is not conductive. It's just cold. And if you pour liquid nitrogen on your hand, okay, you still can stand with it. Although, you may say, oh, it's very cold. And you just pull your hand. And you are not hurt at all in case of liquid nitrogen. Although it's very cold, but still you are okay. So liquid nitrogen is not so dangerous coolant, after all.
Okay, thank you.
Okay. I see more. I see several hands here. Please. You will take a few more questions and we will stop.
Dans le cas d'une coupure de courant dans un objet en déplacement comme le train ou autre chose, qu'est-ce qui se passe? Comment fait-on pour arrêter le train ou un véhicule quelconque?
Yeah, okay. The question, you got the question? So the question is, if there is interruption of the electricity for the train, for instance, what happens when that?
Okay, there are two cases. One is the interruption of electricity in the superconducting magnet. The other one is that you do not get electricity in the coils. And at first, if superconductor loses its perpetual current, then it's like losing the wheels for a train. It's dangerous. Okay? And so the train has wheels, another wheel, another set of wheels. And if the superconducting magnet loses its function, then it touches down on the ground and runs on the wheels, just like airplanes do. Okay, that's one of the answer. And the other one is that if you have AC current changing the polarity of the coils on the side, on both sides, then how it happens is that if you have just conducting coils there without having external electricity, it functions like a brake, because it's a superconducting magnet. So if a magnet moves nearby a metal, then it gets braking function. So it stops.
Okay. We have one last question here. Oh, sorry, I see a lot of hands here.
Well, would you
okay, yes, please go ahead.
Would ask if the global cooperation on research worldwide, how is it going on? Is it just competition for each country, or a kind of global cooperation on research?
So the question is, how does the international collaboration function in the research? Is it just competition between countries, or are they collaborating, or what happens? I think that was the question.
Well, to the stage, where it is still pretty competitive, okay, they all cooperate, like Oystein and me. Okay? That means, we are not doing practical things. Our material is not practical yet. Okay? But when it comes to really practical materials or practical systems, I find that they keep things in secret. For example, in case of JR Maglev, several years ago, I was put on the train, perhaps because they wanted to show that the Maglev is really a practical train. Okay? They wanted to show. But then they changed the system to finalize the structure. And then they did not allow the other people to be put on. And now they have started that again. That means they have become very confident about their practical line.
But that also means that we are getting close to real applications and real business. Yes, one question here.
Hi there. I was wondering if you think there might be a theoretical limit to the productivity or the efficiency of superconductors. Would there be like some, maybe you were hoping for room temperature superconductors, but is it that even theoretically possible?
I think perhaps, this question, he asked me about the probability of finding room temperature superconductor, something like that. Okay. This question is the most frequently asked question and the most difficult question to answer. Okay. And if there are theorists here, I want him to comment on it, but according to my impression is that there are no theorists who can answer this question. And theorists' calculation is such that 3 times, 4 times difference in critical temperature is not a problem at all. Their calculation precision is still very low. So if we can go 3 times more, we can reach the room temperature. Already it's 1/2 of the room temperature. So although everybody wants room temperature superconductor, but there are none who can answer when and with what probability we can find it.
Maybe one can add to that answer that the jump that you heard about in Kitazawa's talk from the very low temperature superconductors to those above liquid nitrogen appeared even more difficult in 1985 than the jump from where we are now to room temperature. So in that sense, it doesn't seem totally impossible. The thing is that we don't really understand the new cuprate superconductors. We don't really know them well enough to be able to predict with a strong probability what would be the highest SOC. And I think that means that the questions are totally open at this point. It could happen tomorrow morning, or it could happen only in 100 years. We are not really able to say that today. That's why we have to continue research in this field.
Yes. In 25 years ago, when Bernoulli and Mueller found cuprate copper oxide superconductor, there are 20 to 30,000 people who started trying to search, mixing various compositions, looking at the element table, mixing copper, oxygen, and something else. And we all did so, but after 25 years, I think we have depleted of thinking, the new combination from the periodic table. But 3 years ago, a person of Tokyo Institute of Technology found that instead of copper oxygen system, he found iron oxygen system, Fe and O. And now they have started doing again the similar thing. But so far, they have not found higher critical temperature than the original one he found. So there may be a possibility in the new material series to find higher critical temperature.
Okay, one question here. Is there a mic?
Bonsoir. Good evening, Professor Kitazawa. Thank you for the presentation tonight. From the presentation, I see that the closest application of superconductivity that affects our daily life seems to be the maglev train. But it seems that the maglev trains are all built on test basis now. There is no wide commercialization of this technology, except maybe one short line in China. So what do you see are the major obstacles that prevent the wide commercialization of this technology? Is it technical in nature, or is it something financial? How long do you see into the future will this technology be widely commercialized? Thank you.
I am not sure whether I should tell the truth or not, but because I'm a scientist, you see, technologically, JR is confident on the present, on maglev technology. But financially, the problem is different. And in case of Japan, we have conventional bullet train service already. And politicians are elected from each district. So each one of them want this bullet train service in their district in order for him to be elected again. Okay? So everyone wants the bullet train, conventional bullet train, but if they put big money on the new maglev line, they have to wait. Okay? So if you ask politicians, they are rather against the idea of introducing new maglev. And that is why Japan Railway Central, that is operating the train from Tokyo to Osaka, they already have the bullet train. So they want another pass. Okay? And for this second pass, they have decided not to ask the politicians to help them, but they have announced by themselves that they spend their own money to open the new trail. And they say that it is 2027 when the new line is completed between Tokyo and Nagoya. But once politicians accept this idea, I'm sure then politicians start pushing them. Why don't you make it earlier? And I think this is their tactics. I mean, JR. Okay.
But I think that the decision that now has been taken is to make a real commercial train and not only a test line. So that step is being taken right now, these days.
So I'm sure that politicians will soon push this plan to make it earlier.
Okay, we had a lot of questions. I will take one more and then we will stop if one. I don't see any hands. Oh, I see a lot of hands up there, but only one. Okay, the one with two hands.
One question.
Okay.
Excusez-moi, je parle malheureusement pas bien anglais, donc je vais la poser en français. Est-ce qu'il existe des applications directes pour le stockage d'énergie grâce à la supraconductivité? Je ne parle pas de faire de l'électrolyse, et stocker sous forme de gaz pour pouvoir retirer de l'énergie, mais stocker directement, par exemple, dans un tore, de l'énergie sous forme d'électrons.
Okay, you got the question?
Yes, it is possible. Because of the perpetual current, you make a big superconducting coil, and you start passing current in the coil, and you then make short circuit of the coil. Then this current, perpetually persists. And when you want to have energy, then you open this circuit, and you get electricity out from there, which was stored in this coil. And in that sense, you can do it, and this is being used in order to prevent the instant cutoff of electricity, instant blackout of electricity for semiconductor companies, where they really need the constant supply of electricity. But the total capacity of energy stored in a superconducting magnet is not very large compared with chemical energy. That's because, in case of chemical energy, this is just like burning oils. This is chemical energy. But in case of superconducting coil, if you pass too much current, this gives you pressure towards outside. Okay? It's like, what do you call this force?
Oh, yeah.
You feel.
You will have if you have a magnet. Sorry, if you have a magnet like this, there are very strong forces due to the field times the current.
Yeah.
So you get a very strong Lorentz force that will tend to make the magnet explode. So you have to keep it. So that makes a problem to make very big storage with that. But temporary storage, for instance, in railway stations, when trains starting in the early morning, then you can, in fact, store energy and then take it out again.
The superconducting magnet is good, for storing a small amount of energy, but response is very quick. But if you want to store too much, then it explodes. Okay? And this explosion force is like chemical bond breakage. So chemical reaction is stronger than the mechanical, mechanical force.
Okay, I don't see any more hands this time. There was the gentleman up there. Okay.
Good evening. Thank you for letting me answer this last question. I'm very fascinated by all these applications that can help to save energy. So my question is very simple. Have you any numbers about how much you save energy with this new train compared with a conventional train?
This new train, Maglev, consumes more energy than conventional bullet train because it runs faster. And all the energy needed to let the train move is because of the air friction. So, it doesn't matter whether it is maglev or a conventional train, how much energy you need to go from Tokyo to Osaka. It all depends upon the speed of the car and the shape of the car in order to avoid air turbulence. And because, the maglev runs faster than the conventional bullet train, that means it needs more energy. So in that sense, it's not energy saving. But compared with the jet plane from Tokyo to Osaka, the maglev consumes 1/3 of the energy the jet plane consumes.
So does that answer your question? It means that actually with these trains you can replace the planes over medium distance. And that will actually both pollution and energy-wise, this is a huge gain. Okay, I think we have had a lot of discussion here. I would like to thank Professor Kitazawa for a very great talk about superconductivity. Thank you very much.
I just want one thing. After the earthquake on March 11th, we have received a lot of help from Switzerland, including the donations and including help team from Switzerland. Just 2 days after the earthquake, they arrived in Japan and helped us a lot. And we have got this sort of help from more than 120 countries. And this help has been big force for the people, who must have been staying in the refugee gymnasium. Although they have moved from this gymnasium to their temporary housing by now, but it still takes at least several years in order for them to move from the devastated area where they got tsunami attacking. So they have to move to the higher place to find the location to make houses. And this is not very easy to let all the people satisfied to choose a new place for them to live. But anyway, they have to do so, and I think it still takes time for them, but they have been very much encouraged by your help. So I'd like to say thank you to you. Thank you very much.